Welcome to the course Design of Reinforced Concrete Structures. In the previous lecture, you have seen the analysis of singly reinforced beams and we have solved a problem on analysis of singly reinforced beams. In today's lecture, we are going to see the design of singly reinforced beams. We are going to solve a problem on the design of singly reinforced beams. Before solving the problem on design of singly reinforced beams, let us follow a few steps. What are the steps you have to follow for designing a singly reinforced beams? So, in the previous classes, we have already discussed what is meant by design. So, in the design, for a given values of grade of concrete, that is FCK, grade of steel, Fy, the breadth and the moment. If all these are given, in some cases, instead of the moment, the load also will be given. If a load is given, what you have to do is, from that load, based on the load, you have to calculate the factored moment. So, based on all these things, given data, what you have to do is, we have to find out the effective depth. The effective depth is nothing but small t, and the area of steel reinforcement. The area of steel reinforcement is nothing but the AST. So, the first step what you have to do is, so what are the unknowns here? The unknown is the effective depth. So, first we will calculate the effective depth D, considering it as a balanced section. So, you have to calculate this effective depth based on the moment what it is given or based on the factored moment. So, how can you calculate it? What is the formula for moment? It is mu is equal to 0.36 FCK B into XU. So, this is the compressive force into the lever arm. The lever arm is D minus 0.42 into XU. So, this is what the formula for moment is, what we have calculated in the previous sections. That is, moment mu is equal to 0.36 FCK B into XU into the lever arm, which is D minus 0.42 XU. As here we are considering a balanced section. So, XU will be, in place of XU, you have to substitute the XU limit. So, the MU limit will be 0.36 FCK B into XU limit into D minus 0.42 XU limit. So, as we have discussed in the previous class, the XU limit value will vary based on the grade of the steel. So, for different grades of steels, the values of XU limit are discussed previously. So, for Fe250, the XU limit value is 0.53D. So, it is Fe415. The XU limit value is 0.48D. And for Fe500, the XU limit value is 0.46D, which we have discussed in the previous class. Now, based on the grade of the steel given, if the grade of the steel Fi is given as 250, what you have to do? You have to substitute the XU limit value as 0.53D in this particular XU limit. In the similar way, if the grade of steel is given as Fe415, then you have to substitute a value of 0.48 here. If the grade of the steel is Fe500, then you have to substitute a value of 0.46 here. Now, for suppose let us consider the grade of steel as Fe250 or Fe400, Fe500. If you substitute all the values here, you will get a certain values of Mu limit. So, for now let us calculate the moment of resistance, okay, by substituting the values of XU limit for different grades of steel. So, if you will substitute the XU limit value for 250 grade of steel, then the moment of resistance, you will get a value of 0.148 FCK B into D square. Then for Fe415, if you substitute the value of XU limit at 0.48 D, then the moment of resistance value will get it as 0.138 FCK BD square. In the similar way, for Fe500, the moment of resistance value will get it as 0.133 FCK BD square. So, based on the grade of steel, you can use these particular equations for finding out the moment of resistance. Now, for suppose here I am considering the grade of steel as Fe250. So, what is the equation what we have? That is Mu is equal to 0.148 FCK BD square. So, in this particular step, what are we calculating? We are calculating the effective depth. That is, we have to find out the D here. So, how we will calculate D? D is equal to root over Mu by 0.148 FCK into D. So, from this particular equation, you can find out the effective depth, or else you can write this equation also as D is equal to root over Mu by Q into FCK into D. Here Q is nothing but the value here, that is 0.148. So, if it is Fe250, you will get the value as 0.148, and if it is Fe415, you will get the value of 0.138, and if it is Fe500, you will get the value of 0.133. That is, the Q values will get as this. So, this is how we have to calculate the effective depth D. Now, we have calculated the effective depth. So, what is the next unknown? The next unknown is the area of the steel. So, in the second step, we are going to find out the area of steel reinforcement. So, the step 2 is to calculate the area of steel reinforcement. So, the steel reinforcement, the area of the steel reinforcement also should be calculated for the moment, for what moment it has to carry. So, it can be calculated by using the equation Mu is equal to 0.87 Fy into AST into D minus 0.42 XU. So, by using this equation, what you can do is, you can calculate the area of the steel. So, what will AST will be? AST will be equal to mu divided by 0.87 into Fy into D minus 0.42 XU. So, from this equation, what you can do? You can calculate the area of the steel. So, after calculating the effective depth and calculating the area of the steel required, then what you have to do is, you have to check the area of steel for minimum and maximum steel reinforcement to be provided. So, the area what you got here, okay, it should be more than the minimum area and it should be less than the maximum area of steel reinforcement. Area of steel reinforcement. So, if the check is okay, then the design is completed. Now, we will solve a problem based on the design of singly reinforced beams. So, here you can see the question, that is, design a singly reinforced beam for an applied factored moment of 120 kilonewton meter. Assume the width of the section as 230 mm and the materials are M20 grade concrete and HYSD reinforcement of grade Fe 4 and 5. So, in this particular problem, he is asking us to design a singly reinforced beam. So, he has given us a data. So, what was the data? So, first we will solve, we will write down all the given data. So, what is the data given here? That is, the moment is given, which is 120 kilonewton meter, and he has given us the breadth of the section, which is 230 mm. In some cases, the breadth of the section will not be given. In such kind of situations, what you have to do is, you have to assume a suitable breadth of the section, and the grade of the concrete FCK is given, which is 20 Newton per mm square, and the grade of the steel Fy is given, which is 415 Newton per mm square. So, this is the given data. So, what are the unknowns here? You have to find out the effective depth and you have to find out the area of steel required for carrying this particular moment mu. So, what is the first step what you have to follow? The first step what you have to do is, we have to find out the effective depth considering the balanced condition. So, previously we have already seen the formulas for calculating the effective depth. So, what is the formula for calculating the effective depth? It is D is equal to root over mu by Q into FCK into B. Here the value of mu is already given and the value of Q will depend based on the grade of the steel, okay, and FCK value is also given, which is 20 Newton per mm square, and the breadth value is also given, which is 230 mm. So, substitute all the values in this particular equation. So, what it will be? Then D will be equal to mu is equal to 120 into 10 to the power of 6 divided by, as it is Fe 415 grade, the Q value will be 0.138 into 20 into, what is B here? It is 230 mm. So if you will solve this particular equation, you will get a value of D as 434.8 mm. Now we have got the value, that is the effective depth for this particular moment as 434.8 mm. So whenever you are designing, consider the effective depth a bit more than this value. I am increasing the effective depth to 5% extra. So increase effective depth value to 5% more. Okay, 5% more you have to increase. So if you will increase this, what you will get the value of effective depth? It is D is equal to 1.05 into 434.8, which will give you 456.54 mm approximately, which you can write it as 460 mm. So the effective depth D is approximately, you can write it as 460 mm. The effective depth value you got is it as 460 mm. Now let us draw the section here. So now what we have already given data is the breadth is 230 mm. Okay, the depth, that is somewhere, if suppose here the reinforcement is there. Okay, so the depth from the center of the reinforcement to the topmost compression fiber is called as the effective depth, which we have discussed previously, and we got this value as 460 mm. Now what is this depth? This depth is nothing but the capital D, which is nothing but the overall depth. So for this reason, to find out the overall depth, what I am doing here is, I am assuming an effective cover of 40 mm. That is the distance from the center of the reinforcement to the bottommost fiber. This part is called as the effective cover. So this effective cover, I am considering it as, or I am assuming it as 40 mm. So what will be the effective total depth D? The total depth D will be effective depth plus the effective cover. So it is 460 plus 40 mm, which gives you 500 mm. So what is the overall depth of the beam now? The overall depth of the beam D is 500 mm. So now we have found out the effective depth as well as the overall depth. So what are the remaining things which are to be found out? The next thing what you have to find out is the area of steel required for carrying this particular moment mu. Now let us find out the area of steel required, that is the step 2. Now the next step is what? It is to find out the area of steel reinforcement required for carrying this particular moment mu. So in the previous topic we have already seen the formula for calculating the area of the steel. So the formula is mu is equal to 0.87 Fy into AST into D minus 0.42 into XU. Now here the value of mu is already given, 120 into 10 to the power of 6 is equal to 0.87 into Fy. What is Fy? It is 415 into area of steel. This is what we have to find out now. And the D is also we have calculated previously, which is how much it is? 460 mm. That is the effective depth is what you have to consider here. Minus 0.42 into XU. Do you know the value of XU? So here I am writing the value of XU as XU is equal to 0.87 Fy into AST divided by 0.36 FCK into B. This one is the neutral axis depth value, which we have already derived in the previous classes. So, in place of XU, I am going to substitute this particular equation here. So, 0.42 into 0.87 into Fy into AST divided by 0.36 FCK into B. So, you already know the value of Fy which is given here. AST is what you have to find out. You already know the value of FCK and you already know the value of B. Substitute all these values here. 120 into 10 to the power of 6 is equal to 0.87 into 4 and 5 into AST into 460 minus 42 into 0.87 into Fy is 415 into the area of steel is what it is required into 0.36, FCK is 20 into B is 230 mm. Now, if you solve this whole equation, you will get a value of the area of steel which is equal to 874 mm square. So, this is what the required area of steel for this particular moment of 120 carrying this particular moment of 120 kilonewton meter. So, now the next step is to check for the minimum and maximum area of steel reinforcement which is required. So, now let us check for the minimum and maximum area of steel reinforcement. So what is the AST which is required? The required AST is 874 mm square is what the required AST is. Now, we will check for the minimum area of steel reinforcement. So, in the previous classes we have already discussed the formula. What is the formula? That is A naught by BD is equal to 0.85 by Fy. We already know the value of B, the value of D and also the value for Fy. Substitute all the values here. So, A naught is equal to 0.85 into B is 230 and D is 460 divided by 415. By solving this, you will get a value of 216.69. So, how much is the required? It is 874 mm square. Here the minimum is 216.69 mm square. So, it is okay. So, the design is okay. So, this is how we have to check for the minimum area of steel reinforcement. Now, let us check for the maximum area of steel reinforcement. So, what is the formula? It is the maximum area for the steel reinforcement is 0.4 B into D. So, 0.4 into B here is 230 and D is nothing but the overall depth of the beam. So, overall depth of the beam is how much? It is 500. So, if you will solve this, you will get a value of 4600 mm square. So, this is the maximum area of steel reinforcement which is to be provided. So, okay, hence the check is okay. So, this is the minimum, okay, this is the required and this is the maximum area. So, always this required AST should be in between the minimum and the maximum area of the steel reinforcement, hence the design is okay. Now, what we have found out? We have found out the area of the steel required. So, now we have known the breadth of the beam, the depth of the beam is also known and the area of the steel required is also calculated. But here what we have to find? We have to find out the what should be the number of bars which has to be provided and what should be the dia of each bar is what we have to find it out based on the AST what we have calculated. Now, let us assume the dia of bar be 20 mm. Now what I am assuming is, let the diameter of the reinforcement bar be 20 mm. So now I will calculate the number of bars to be provided. So let n be the number of bars to be provided. So n into pi d square by 4 is equal to the area of steel, which is 874 mm square. Here I have assumed the dia of the bar as 20 mm. So n into pi into 20 whole square divided by 4 is equal to 874. So from this you can calculate the value of n. The value of n is 2.78. That is the approximately you can take it as the number of bars as 3. So what you have to do? You have to provide the number of bars as 3 and the dia of the each bar as 20 mm. So now you can do one more thing also. What you can do? You can find out the area of steel which is provided. So here it is what the area of steel which is required. For the required area of steel, number of bars what you have got is 2.78. But you cannot provide 2.78 bars. So for that reason what I have done is I have approximated it to 3 number of bars. So if you have provided 3 number of bars, what it will happen? That is, you have increased the area of steel which has to be provided. So by keeping the number of bars as 3 bars, you can also find out the area of steel which is provided. So in this way, you have to design the singly reinforced beam.